Good evening then, everybody. Welcome to this live stream, which is a look at the AQA A Level Chemistry required practicals. My name is Mr. Smith, and I'm going to talk you through some of the key things regarding these practicals, some of the things that I think you need to be aware of. So we're going to begin by just going through the 6 required practical activities for AS Chemistry. I know there are people who are a little bit unsure of how apparatus error works, so we'll run through a few examples of that. And we'll look at some examples of questions from the specimen papers. In terms of my background, obviously I teach A-level chemistry AQA. I've worked as an examiner, but I haven't worked as a question setter in the past. So if I happen to stumble across something that does turn out to be in the exam, it's purely by accident. I have no inside information. I just really want to make that clear. Okay. So these are the 6 required practicals that you will do at some point during your first year in A-level chemistry. You will have done some of these already. There may be some still to come. I imagine that early in the year you made up a volumetric solution and did an acid-base titration to determine the concentration of a solution for which you did not know the concentration of. You will have measured an enthalpy change, probably fairly recently. Investigating how rate of reaction changes with temperature, something that you may have done or you might be moving on to quite soon. Then we have the test tube reactions. These are similar to test tube reactions you've done at GCSE. Some of them are a little bit more involved. We'll come on to that as well. Distillation of a product from a reaction and the organic test, the test for the alcohol, aldehyde, alkene, and carboxylic acid functional groups. Okay, just as something to really be aware of when you're doing practical work, these are things that you should really consider, things that you should really be thinking about. You should ask yourself, if you know how to carry out a practical, could you describe to somebody else how to do it if you had to? A couple of the specimen papers have questions like this, which we'll come to a bit later on. And in addition to being able to talk about what you're doing, can you explain why you're doing what you're doing, which is just as important. And in many cases, your results from your experiment require some kind of mathematical manipulation. So the next question that you should be able to ask yourself is, can you actually carry out an analysis of your results? Now, this is a document which will be very, very useful to you. I don't know if you've come across this at all. You can find it on the internet. I'm going to refer to it during this presentation, so you don't have to worry about bringing it up in front of you right now. It's the AQA A Level Chemistry Handbook. There are a number of handbooks. There's a general A-level science handbook, and then there are separate handbooks for chemistry, biology, and physics. So if you're doing the other science A-levels, they're definitely worth a look as well. I'm going to refer to this as we go along, because for every required practical, there's an example, an exemplar practical there, which will be very similar to the one that you will have done, or the one that you are going to do. It may be slightly different. That's not too critical for reasons that we'll explore as we go along. But this is a document that we will use quite a bit today, and I'm sure you'll see how useful it is. Okay, so let's begin by just going through each practical one at a time. Look at the main points, the main features that you need to be aware of. So the first one, making up a volumetric solution and carrying out a simple acid-base titration. You should be able to describe how you would do this. You should be able to identify concordant titers from your results and calculate the mean in the correct way. And you should be able to use your mean titer to determine the concentration of a solution, to determine the concentration of an unknown. What I'm going to do at this point then is refer you to the practical handbook. So I have it just here. Hopefully it's appearing on your screen now. I'm actually watching what you're watching, so I can see when things are appearing as they should be. So this document, and you saw the link before, when you go back and refer to the video, you can pause it and find it again. We're on page 80, and we have here an exemplar for this required practical, making up the volumetric solution, carrying out a simple acid-base titration. Now, in this case, it's sodium hydrogen sulfate. But one of the nice things about these required practicals is that there are many, there are some variations in the process, but there are plenty of variations in terms of the chemicals that you might use. So it doesn't have to be sodium hydrogen sulfate, but it's a good example of one to use. It tends to be a fairly stable compound, so you can do the titration, say up to a week later, and you should get reasonably good results. So this is an example procedure sheet that you might get, a method sheet. You're provided with, there is your apparatus, so fairly straightforward, weighing bottle or boat, your volumetric flask, your compound of course, filter funnel spatula, deionized distilled water, beaker, glass rod, and a balance reading to 2 or 3 decimal places. Diagrams provided in case you don't know what those things look like. And let's have a look at the suggested method. This is a fairly standard method. I think it's pretty much a straight lift from the ones that they used before they changed the spec, so it's really quite straightforward. Things to be aware of, well, when you're making a standard solution, you are aiming for a particular concentration, but you usually allow a range. You're aiming for a concentration within a range, and that's because if you've got an idea of the concentration of the solution that you're trying to determine, you've got a ballpark idea, then you don't need a very, very specific concentration for your standard solution. As long as your standard solution is in a reasonable range, then you can get a result that is acceptable. Now, for the method described here, you're not going to be able to make up a standard solution of a very, very specific concentration, and I'll explain why. If you have a look at point A, calculate the mass of sodium hydrogen sulfate solid needed to produce a 1 mole per decimeter cube solution. So that's what you're aiming for. Now, what you should find is that the mass required is around about 3 grams, and they are instructing you to weigh between 2.7 and 3.3. If you're using the monohydrate, the mass to weigh out should be between 3.1 and 3.8. In case you're wondering what the monohydrate is, you should have come across hydrated solids. Basically, they have this entity called water crystallization. There are a number of water molecules associated with the compound. In the case of sodium hydrogen sulfate, the monohydrate contains, as you can probably guess from the name, 1 water molecule per mole, or 1 mole of water molecules per mole of sodium hydrogen sulfate. And any mass within that range will give you a concentration of between 0.900 and 0.110, which is considered acceptable in this case. So the procedure here, you will have done this. You may not have done it exactly this way, I'll come to that in a minute, but the procedure is described here. Weigh your weighing bottle on your digital balance, use the spatula, place the approximate mass of sodium hydrogen sulfate that you've calculated to be necessary. So if you've calculated 3 grams, 3.0 grams, you place about 3.0. If it says 2.9 or 3.1, that should be okay. You don't have to get it at exactly 3.0. You weigh the weighing bottle, part D. You weigh the weighing bottle in its contents accurately, record the precise mass. Then you transfer the contents into a beaker and reweigh the weighing bottle, which may still contain traces of sodium hydrogen sulfate. Now that's absolutely fine, because what you can do then for part F, after you've reweighed, you can determine exactly how much sodium hydrogen sulfate has gone into the beaker. So if you weighed, for example, 3.00 grams, and you transfer it across and there's 0.01 grams left, you know that there are 2.99 grams that's actually gone into your beaker. And you've failed to transfer 0.01, but that's absolutely fine, because 2.99 is within your acceptable range, so that's okay. The important thing is that you know exactly how much has gone into the beaker. This technique is known as it's determining the mass by difference. Now it says here you add distilled water. Because you're making up a 250 centimeter cube solution, adding 100 of deionized water is absolutely fine. The purpose of this is to dissolve the solid. before you transfer it to your volumetric flask. If you don't think it's all dissolved and you need to have more than 100, that's fine, as long as you don't get too close to the 250 that you're trying to make it up to, because there's a danger that you'll overshoot your mark when you transfer it all to your volumetric. Now, a point to make just before we move on too far, as an alternative to working out the difference by mass, once you have transferred the contents of the whey bottle into a beaker, one option that you've got is to get your wash bottle and actually very carefully rinse the contents of the whey boat into the beaker. And by doing this, you ensure that you transfer all of the solid. As long as all of the washings go into the beaker, you use plenty of deionized water, plenty to ensure that all the washings go across, but not so much that you're in danger of adding more than 250. That's absolutely fine. You can do it that way too. They are both acceptable methods. It's a matter of preference. Either is fine. Entirely up to you. Okay, so if we go to point G, you've just talked about this. You want to make sure it's all dissolved, and then you transfer the beaker to your volumetric flask. Use a funnel, of course, so that you don't run the risk of spilling any of your compound. And then you use your distilled water wash bottle, rinse the beaker, rinse the funnel, make sure all the washings go in, rinse the glass rod as well. You've used that to stir the solution and to make sure it's all dissolved. Make sure you wash everything with plenty of water. Once you've done all of your washings, you might be quite close to your 250 mark, but then you just make it up. So you make it up to the mark, make sure you don't overshoot. If you overshoot, you've basically got to start again. Stopper, make sure it's thoroughly mixed. So give it a good shake or invert it, make sure the stopper is on, of course. And then you can work out the exact concentration in moles per decimeter cube using your actual mass. And that's it. That's how you do it. So that's making up the solution. Then you've got your titration. Well, if we scroll it down a little bit, that's actually the teacher's notes, so don't need to worry about it too much. It tells you that you're going to determine the concentration of a solution of sodium hydroxide. So that tells you that your sodium hydrogen sulfate must be an acidic solution. It is. It's a weakly acidic solution, so you can use sodium hydroxide to neutralize it. I'm not going to go through every single point here because I think you've done these before often enough. But you take your standard solution of sodium hydrogen sulfate, you pour some of it into a beaker, and it says rinse the burette. So you're going to put the sodium hydrogen sulfate into your burette and rinse it through. Because you've made up 250, in theory that's enough for approximately 10 titrations. You're hoping that it will take you no more than 4. So you can afford to lose a bit of the solution washing through the burette, that's fine. And then your sodium hydroxide of unknown concentration, 100 into a beaker, and then pipette it. Pipette 25 into a conical flask, which has been pre-rinsed with deionized water. It doesn't actually matter too much if there's a little bit of deionized water left in your flask, because you're still going to have the same number of moles of sodium hydroxide going into it, so it shouldn't affect your titer value. 2 to 3 drops of phenolphthalein in the conical flask. A couple of phenolphthalein in alkali. This might be an opportunity for you to answer a question. You can send it to everybody or just send it to me if you wish. Colour of phenolphthalein in alkali. I'll give you a moment on the text box. We'll see who is first to come up with the answer. Anybody? Excellent. Answers are coming through. Bright pink. Absolutely right. Good. Right. So moving on. Yeah, construct the table and then titrate. A word on the burette. When you fill the burette, there is a gap where I'm holding my cursor down here between the burette tap and the tip of the burette. That should be full of liquid. The reason being that if there is air in there, then that will affect your burette reading. That's something that we will come back to later on. So If we just move it on a little bit, let's have a look at some of the results that you might get. Here are some of the results. Good chance that you, oh, sorry, I'll move that back up a bit. Good chance that you might be asked to analyze or process some results. So you should know that here are your results, initial, final, titer. You should know that concordants are meant to be within 0.10 of each other. And if you calculate an average, the average should be to 2 decimal places. Remember that you can give your burette readings to the nearest 0.05, even though they measure to 0.1. We'll look at this a little bit later on, but you can give the value as 0.05. You can make a determination between 2 graduations on a burette. If you have a value of, say, 25.05 and 25.10, the average 2 decimal places will be 25.08, and that's a perfectly acceptable value to give. So a little bit later on, we'll have a look at some example questions. There are 1 or 2 from the specimen paper that deal with this, so we'll come back to that later. It's actually first practical. So let's move on to the second practical. Just go back to my presentation in a moment. So we've had a look at that. Measurement of an enthalpy change. I imagine you've done a few of these. There are lots that you can do. You can do neutralization of acid and alkali. That usually has an energy change associated with it. Displacement reactions between copper sulfate solution and zinc are also quite popular. You can do the burning of an alcohol to heat water, but as I'm sure you will know, if you've done this, you get terrible heat losses and the results are not terribly reliable, so it doesn't work as well as you might like. Now, there is a really good example in the practical handbook, so let's have a look at it. Move past all this, not too worried about that. This is a really good one because it, addition to enthalpy change, it also requires knowledge of Hess's law. I use this one myself. The conversion of hydrated copper sulfate, anhydrous copper sulfate to hydrated copper sulfate. So anhydrous copper sulfate is white, has formula CuSO4. Hydrated copper sulfate, they're the blue crystals with formula CuSO4.5H2O. Now, you can't measure delta H3 as written here directly, but what you can do is dissolve anhydrous copper sulfate in water and hydrated copper sulfate in water, and they will both form copper sulfate solutions. So you have the basis of a Hess cycle. So if you can measure delta H1 in kilojoules per mole and delta H2 in kilojoules per mole, you can determine delta H3 using Hess's law. That's the idea. So if we move it on a bit, you will have done these before, I'm sure. You'll be familiar with this. Essentially, you weigh an amount of the solid, a sensible amount of the solid, to give you a reasonably big temperature change. So you want to be able to measure a reasonably big temperature change. That reduces the experimental error, which we'll talk about later. But you don't want to measure an amount that is so big that it takes it above and beyond the solubility of the compound, because then obviously you're not going to get accurate results. So you'll be familiar with this. You add your solid. You don't add your solid. You determine the temperature of the water beforehand for a couple of minutes, 2-3 minutes perhaps. Then you add the solid on minute 4. You give it a really, really good mix, and then you determine the temperature 4 times every minute up to, say, 15 minutes. There you go. 4 per minute. Add the anhydrous copper sulfate. Don't measure the temperature at that time, and keep measuring the temperature every minute until you're done. Hydrated copper sulfate, exactly the same. So in terms of calculations, you need to be able to work out the heat change of the reaction. We'll look at the graphs in a minute. Heat loss to surroundings is ignored. The specific heat capacity of the polystyrene cup is considered negligible compared to the water. So essentially, you can usually get fairly good results by doing this particular experiment. And I reckon you've probably done all these calculations before, or calculations like them. But if we just go back to the actual experiment in a minute. These are typical of the types of graphs that you're going to get. These are actually taken from the data that's supplied here. So the first reaction, if we have a look at the data, move right down, you can see that's experiment 1, so that's the anhydrous copper sulfate. It's an exothermic reaction, and you would expect the temperature after the reaction to drop and to continue dropping. This is a little bit of a surprise over here. If you have a look at the results on the graph, you can see that they are leveling out. You wouldn't expect them to level out until the temperature drops significantly more, because we're above the initial temperature here. So as long as the surrounding area has stayed the same temperature as before, around about just below 20 degrees, you'd expect this to continue to drop off. So I've drawn the line of best fit to kind of reflect the trend that we are expecting. For the other reaction, the dissolving the hydrated copper sulfate, you can see it's endothermic. We have a temperature drop and it stays steady. Again, that's a bit of a surprise, really. You would expect it to start gradually increasing. But you can only go off the data you've been given, so that's how you determine your energy change there. So you have a delta T for reaction 1, a delta T for reaction 2. You can work out the energy change in joules, and you use your mass of anhydrous and hydrated copper sulfate to work out the moles, and you can work out the energy change in kilojoules per mole. I think with these sorts of practicals, I think you're more likely to be asked about accuracy and temperature change considerations. When we have a look at the specimen questions, you'll see what I mean. So we'll move it on. Rate of reaction changes with temperature. I'm not going to spend too long on this one. Again, you've probably done this, so you're about to do it. The example given is a classic example. It's certainly the one that I use, and it's the sodium thiosulfate example. I'll just bring it down a bit. So hydrochloric acid, sodium thiosulfate. Point to make, just in case you don't know this, the thio part of a compound. Thio is used to indicate that an atom of oxygen has been replaced by sulfur. So sodium sulfate would have the formula Na2SO4. If you take away an oxygen, replace it with sulfur, you end up with thiosulfate S2O3. Just in case you didn't know that, that's what it is. Reacts with hydrochloric acid to give sodium chloride, sulfur dioxide, and sulfur solid. And that's the important part, because of course it is a solid. You're dealing with compounds in solution, so that tells you that the sulfur must be insoluble, and indeed it is. It's insoluble in water. And as the sulfur is generated, it makes the solution opaque, so you can't see through it. So what do? You put a cross underneath your reacting mixture, you look above it, and as time goes on, it's harder and harder to see the cross, and you time how long it takes for the cross to disappear. It's one that we're all familiar with. Now, suggested temperatures. Controlling the temperature of this experiment is difficult, but you don't have to get the temperatures absolutely exact. Point worth making, it says here, don't exceed 55. If you go above 55, then obviously the reaction will be faster. One of the products is sulfur dioxide gas, which can exacerbate asthma conditions, so that's why you mustn't let the temperature get too hot. Otherwise, there's a danger people will start to choke because of all the sulfur dioxide that's being made. Measuring the temperature is difficult. The suggestion here is that in the method it says use 10 centimeters cubed of hydrochloric acid and 10 centimeters cubed of sodium thiosulfate, and heat one of them or both of them in a water bath and use the mean temperature if you heat one and not the other to work out or estimate the temperature of the whole thing. So you have a suggested method here. I'll let you read this at your own leisure, really. There isn't too much more to say about it. Again, I think the main considerations here, I think the type of questions that you might get asked will relate to ensuring that your results are as accurate as they can be. So I think what we'll do, we'll move straight on to the next one. Test tube reactions to identify cations and anions. You may or may not have done all of these yet. There are quite a few different tests that you need to be aware of. I think the main thing is that you are aware of the observations and the best way to describe the observations. So we'll come to that in a minute. But group 2 ions, if you haven't done these yet, you can use sodium hydroxide solution and in a separate test dilute sulfuric acid solution and observe the precipitates, and there's a particular trend. The group 2 ions with sodium hydroxide become more soluble as you go down the group, and with sulfuric acid they become less soluble as you go down the group. So group 2 hydroxides increasingly soluble down the group, group 2 sulfates decreasingly soluble down the group. Ammonium ion, any ammonium salt solution mixed with a little sodium hydroxide and heated gently will turn damp red litmus paper blue as a result of the production of ammonia. Group 7 ions, you'll have come across this at GCSE, dilute nitric acid followed by dilute silver nitrate solution. You can use ammonia for an additional evaluation. You must add dilute nitric acid first because, again, as you know from GCSE, you get a mixture of precipitates, white, cream or yellow. But if you fail to add the dilute nitric acid, the silver nitrate can produce precipitates with other ions like hydroxide and carbonates. You can get a false reading. The nitric acid is used to remove any of those ions that you don't want there. That could give you a false reading. Test for hydroxide, just use of red litmus, that's absolutely fine. Carbonates, dilute hydrochloric acid, should produce carbon dioxide, so you bubble the gas produced through lime water and turn the lime water cloudy. And sulfate, dilute hydrochloric acid followed by barium chloride. The dilute sulfuric acid required for exactly the same reasons you need dilute nitric acid before silver nitrates to remove any ions that could give you a false reading like carbonate ions. So as I said before, I think the key thing here is taking care with your observations. So again, I'm going to go back to the handbook because on the next practical, I'll find it in a moment. They have tables of results and they talk you through essentially exemplar results. Here we go. So I said before that group 2 ions produce precipitates with sodium hydroxide and sulfuric acid. The reason why it's worth doing both tests is that the results are sometimes a little bit unreliable. What you are meant to see, and rather unhelpfully, these have not been put in group order, but magnesium chloride should have the clearest precipitate, followed by calcium bromide, and then the strontium salt will may have a little bit of precipitate and the barium salt will have no precipitate. But sometimes it's hard to distinguish between some of them. So here you can really be able to tell which one was calcium and which one was strontium from those results. You can't really see which one is the most soluble. So if we use it in conjunction with the sulfate, barium chloride will produce a really obvious white precipitate. Magnesium chloride, no solution at all. And often with the sulfate, you do see a difference between strontium and calcium. Strontium will produce a reasonably good precipitate. Sometimes strontium is hard to distinguish between barium. But between both of those tests, hopefully you'll be able to distinguish which one's which. Questions just come through. How would you describe observations? Would you literally say what you see, or would you have to elaborate? If it's a simple test tube reaction, I think the main thing is, when it comes to observations, is that you describe any changes that take place. So if you see a white precipitate, that is absolutely fine. You can say a white precipitate. It's not being done here, but it's often good practice to describe the before and after. So, so something like white precipitate formed from colourless solution, for example, that makes it really clear what it looked like before and what it looked like afterwards. So I think that's the main thing, describing observations. Yes, literally say what you see. Terminology is the key thing. Use the right terminology. So cloudy and milky are words that we really want to avoid now. We want to talk about solids that have formed within liquids as precipitates, and use that word precipitate, and use really, really definite colours. Another quick example, well actually, I'll say another quick example, we'll have a look at bit further down. I'm thinking of the bromide precipitate that forms with silver nitrates. It's a cream precipitate. Some people call it a creamy precipitate, which is a bit dodgy. You should call it a cream precipitate. The ammonium chloride, really clear. That red litmus paper turns blue. Sodium hydroxide and ammonia will do the same thing. That red litmus turns blue. Sulfate ions, white precipitate forms. Lime water will turn cloudy for positive tests. Okay, now this one's worth a closer look. This is your silver nitrate test for the presence of chloride, bromide, and iodide. With nitric acid followed by silver nitrate, get a white precipitate with chloride, cream precipitate with bromide, yellow precipitate with iodide. I'll say it again, call it cream, don't call it creamy. You're asking for trouble if you do that. Now, sometimes it's hard to tell the difference between the colours. You can use dilute and concentrated ammonia to help you here, because potassium chloride, the precipitate that's formed, the silver chloride, the white precipitate, will dissolve in dilute ammonia. The silver bromide and the silver iodide do not dissolve in dilute ammonia, so they'll still be there. But if you use concentrated ammonia, again, any silver chloride that's formed will dissolve really, really easily. The silver bromide, the cream precipitate, will also dissolve in concentrated ammonia. The yellow precipitate of silver iodide does not dissolve in concentrated ammonia. So that can be used as an additional test to distinguish them. Now, just briefly, I'm not going to dwell on this because this is something that you're probably not going to look at until towards the end of the year. But you can also use concentrated sulfuric acid on solid salts of chloride, bromide, and iodide, because the bromide and iodide actually liberate bromine and iodine. So you can see observations that relate to those as well. In terms of distinguishing the ions, concentrated sulfuric acid is not required. It's an additional test that you need to be aware of, and you will learn about it in due course. And if you're asked to determine solutions of these ions, chloride, bromide, iodide, using nitric acid, silver nitrate, and ammonia will get you the information that you need to be able to do that. Okay, so two more then. We'll have a look at both of these. Distillation of a product from a reaction. It doesn't really matter what product it is or what reaction you've done. There are a couple of examples in the handbook. But I think here the main thing is that you're really clear on the actual procedure for doing a distillation. You may be asked to draw a diagram, you may be asked to describe it, you may be offered the opportunity to do both. When it comes to the diagram, a couple of things to be aware of. Make sure that the water inlet of your condenser and the water outlet are not sealed, they are open. And make sure that the end of the condenser is also open, so that's where the liquid can come through. In this whole piece of equipment, the only part that is open is the end of the condenser. That's the only place where the chemicals can come out. And of course, you've got the inlet and outlet for the condenser as well. Now, if you are collecting very volatile compounds, then your collection vessel will also need to be cooled in some way. A good example would be collecting, say, ethanol, which has a boiling point in the 20s Celsius. So there's a danger that it could evaporate once it's collected. If you use a cooled collection vessel, then that problem won't arise. Quick word on the fractionating column. It's a piece of apparatus that I think most schools don't routinely use because they don't tend to have many of them. But if you're lucky, you'll see it demonstrated. Its purpose is to essentially give you improved separation of the compounds. If you are heating very, very volatile compounds, they're going to vaporize immediately. And if their boiling points are fairly close, there's a danger that they won't separate very well by the time they get to the condenser and they'll come through together. The fractionating column has a temperature gradient, so it's warmer at the top and cooler at the bottom. And it consists of a series of glass pieces or spars. And the idea is that when the vapors hit them, if it's cool enough, they will condense and fall back down. If you didn't have this piece of equipment here, then the danger is that you won't get as good separation. So fractionating column helps you to get a better separation. It's a perfectly acceptable piece of apparatus to use in the laboratory. If you've not done distillation of a product yet, you will do it soon. But this diagram is probably one that you need to have in mind in case you are asked to describe how to do a distillation process. Okay, so moving on. Last practical. Test for alcohol, aldehyde, alkene, and carboxylic acid. I've actually summarized all of these different chemical tests for you on my website, so you can see them all. They are covered in the practical handout as well. As I suggested before, describe all colour changes in full. If you think there is absolutely no change, don't say nothing happens, okay? The phrase to use is no visible change if you think that absolutely nothing happens. But I've summarised all of those different tests for you on my website, so you can actually see them all and make sure that you're aware of them. This is a practical you've probably not done yet, so you've maybe only done it in part. You will get to have a look at all of those. If we just go back to the lab book for a moment and look at how they suggest you do these. Okay, test for alcohol. Metallic sodium. Sodium works very well for all alcohols. It produces hydrogen gas. There's a drawback here, and the drawback is that carboxylic acid will produce the same observation. So if you are trying to differentiate between an alcohol and a carboxylic acid, that's not going to work very well for you. If your alcohol is primary or secondary, you can oxidize it with acidified potassium dichromate, which will change colour from orange to green for a primary or a secondary alcohol. So that's how you could differentiate between them. They are summarised on my website, so you can have a look there. Aldehyde, you can use Phthalate solution, which will give you your brick red precipitate, or you can use Tolland solution, which will give you a silver mirror. Alkene, of course, bromine water, which will decolorize. Carboxylic acid, sodium hydrogen carbonate suggested here. Any metal carbonate or hydrogen carbonate will work fine, and you'll see the effervescence of the production of carbon dioxide. If you wanted to confirm it's carbon dioxide, you'd of course collect the gas, put it through lime water. Halogenol-alkane, they will undergo a hydrolysis reaction with sodium hydroxide, and that will liberate the halogen atom as a halide. So chloride, bromide, or iodide, and then you can use your nitric acid silver nitrate solution. You know the observations for that, and that's how you can do those chemical tests. Okay, so those are the practicals. What I want to do now is move on to calculating apparatus error. And again, the chemistry handbook is our friend. I'm going to go all the way back up to page 56 of this document, because it talks you through it really, really well, actually. Tells you everything that you need to know. Okay. Before we do, you need to know the difference between a reading and a measurement, and we'll have a look at some examples of calculating the percentage error of a piece of equipment. So just move back up a bit for a moment. Okay, so it starts on page 52 of this document. Every piece of apparatus has some uncertainty. Sometimes it tells you what the uncertainty is on the apparatus. Sometimes you need to determine it yourself. The good news is, in the exam, they're quite kind to you, in that they make life a little bit easier for you in general. We'll see what that means in a minute. But the difference between a reading and a measurement. Readings are values found from a single judgment. A measurement is taken as the difference between two judgments of two values. So a thermometer you can assume that the zero has been correctly set. So when you read off a thermometer reading, it's only one judgment, the height of the liquid. But if you use a burette or a ruler, you've got the start point and the end point as two separate readings. So you have a measurement and two uncertainties there. There's an example here which illustrates it quite well using a ruler. This is a good rule of thumb for when it's a one judgment and a reading, or two judgments and a measurement. So for the kinds of equipment you'll be using in AS chemistry, a thermometer, top and balance measuring cylinder, volumetric flask, a single judgment, a single reading, two judgments, stopwatch, because you've got the start and the end, and a burette. So those are the ones that require two judgments. So generally speaking, the uncertainty of a reading using a particular equipment is plus or minus half of the smallest division or greater. So if you're using a thermometer where the graduations are 1 degree Celsius apart, the uncertainty is plus or minus 0.5. Now, here's an example using a ruler, and this applies to a burette as well. If you're measuring an object, you take the measurement of the start of the object here, you take a measurement of the end of the object here. So the area of uncertainty applies at both ends, the start and the end. Now, if this is, for example, a 1 centimeter ruler, the uncertainty for each measurement is 0.5, but you add them together, which will give you an uncertainty of 1 centimeter cubed for using the piece of apparatus. So as it says here, the initial value uncertainty applies to any instrument where the user can set the zero and you could potentially set it incorrectly. But balancers and thermometers are taken to be set with a correct zero, so it doesn't apply to those. Okay, so like I say, this document is really useful to help you with that. And I want to bring it to this paragraph here because this is important for you. Uncertainties and given values. In written exams, students can assume the uncertainty to be plus or minus 1 in the last significant digit. So if a boiling point is quoted as being 78, the uncertainty can be assumed to be plus or minus 1. It may be lower, but without knowing the experiment, the procedure, there's no evidence to assume otherwise. We'll have a look at a couple of examples of questions in a minute, and you'll see that the uncertainty is often quoted. So it gives you a reasonably good indication of what you are dealing with. Okay, so with that in mind, let's just have a look at a couple of examples. And what I'm going to do is actually bring up my presentation because I want to give you the opportunity to do a couple of calculations yourself. So hopefully you've got a calculator and a pen handy. So here we go. We've looked at that. I've taken this from one of the AQA A Level Chemistry textbooks by McFarlane, Quigg and Henry. How do you work out the percentage error of a piece of equipment? Well, it's the error divided by the quantity measured multiplied by 100. That gives you the percentage error. That's all there is to it. So if you're using a pipette and it's a 25 centimeter cube pipette, and the percentage error is plus or minus, or sorry, the margin for error is plus or minus 0.03, what will be the percentage error of that piece of apparatus? I'll give you a moment and see if you can work that out. It didn't take very long. Okay. I'll give you a moment just to see this for yourself. For two readings, it would be double that. That's a question that's just come through. Yes, it would. Technically speaking, it would be. But you wouldn't normally, I guess if you say wanted to pipette 50, so you pipetted one lot of 25 followed by one lot of 25, then yes, the error would be doubled. But of course, if you wanted to pipette 50, you'd use a 50 centimeter cube pipette. But yeah, that question for two readings would be double. That shows you've really got the idea of what we're talking about here. Okay. So yes, indeed, answer came through. It will be 0.12%. It's 0.03 divided by 25 multiplied by 100. 0.12%. Okay, let's have a look at a burette then, because these are a little bit more involved. you may well be given the error to deal with in the exam, but let's assume that we're doing it from this information here. Burette has an error plus or minus 0.05. In a titration, the initial burette reading was 0.05. The final reading was 24.55. What is the percentage uncertainty in the titer value? Again, I'll give you a minute or so and see if you can come up with the answer to this. What would be the percentage uncertainty in the titer value? Okay, so here we go. First of all, you have to work out the titer value, which is the difference, the final minus the initial, which would be 24.5. Now, because you are taking a measurement, you're taking an initial reading and a final reading, the error will be double the error that's quoted. So the error will actually be 0.10. So 2 times 0.05, 0.10, divided by 24.50, multiplied by 100, it comes out as 0.4%. So one answer came through, and that was pretty much spot on, actually. Thought it might have been wrong, but no, you got the right idea there. Now, there's a point that I can make which sort of really homes in on this idea of error, and it's the kind of thing that I get the impression that the exam board are looking at. What if you had a different average titer? What if your average titer, the titer that we're using was not 24.5? What if the titer value that we were considering was just 8.80 centimeters cubed? What would be the percentage uncertainty in this case? Okay, I'm going to give you a moment to try and work this out, and hopefully it will bring home quite an important idea when it comes to considering percentage error of apparatus. We'll wait for a moment and wait for an answer to come through. If you don't want to send the answer to everybody, you can send it just to me. Okay, so here's a calculation. Same as before, but we're using a different value for the titer. So it's 2 times by 0.05, this time divided by 8.8 multiplied by 100. So now the error is 1.1. So the volume of the titer will affect the error. This is why when you do titrations, we look to give you, or you look to achieve volumes that are of the order of 25-ish. That gives you a percentage error, which is usually quite small, as you can see, in that case, 0.4. If you use much smaller titers, your error is bigger. That's an important point, because if you were to do a titration and your titer values are relatively small, you could alter the concentration of your standard solution, or use a standard solution of a smaller concentration to give you bigger titer values and reduce your error. It's quite an important point, and one that has come up in a couple of specimen paper questions. One more thing that we're going to check, multiple measurements. So we have a situation where some crystals have been heated. Again, this is from the textbook that I quoted before. So before heating, they had a mass of 23.45. After heating, they had a mass of 23.21. The error of the balance has been quoted as 0.005. So what is the percentage error in mass lost? I'll talk you straight through this one. Because you're making multiple measurements, the error margin is counted twice, so you have to double it. The mass loss is 23.45, subtract 23.21, which is 0.24. So that brings you to a percentage error in mass loss of 4%. It's 0.010 divided by 0.24 expressed as a percentage, so it'd be 4%. Okay, so what we'll do now, we'll have a look at a few examples of questions. We'll maybe not do all of these, maybe just pick one or two of them for examples, and you can look at the rest at your own leisure. These are from the AS specimen paper. Paper 1, 2, and 3 has lots of examples of questions that look at this sort of thing. So we'll have a look at the first one. So 5.2, this goes back to our silver nitrate test. We'll maybe go up to the top of the question just to give you the full context. Chemical properties of chlorine, sodium chloride, and sodium bromide. The first one's about the reaction with concentrated sulfuric acid, which again at this time of year you might not have talked about yet, so you might not be aware of. So 5.2, colour solution contains a mixture of sodium chloride and sodium bromide. Using aqueous silver nitrate and any other reagents of your choice, develop a procedure to prepare a pure sample of silver bromide from this mixture. Explain each step in the procedure and illustrate your explanations with equations where appropriate. So, your solution's got sodium chloride, sodium bromide. You're being asked to prepare a pure sample of silver bromide. It's worth 6 marks. How would you go about it? Well, let's have a look at what the mark scheme says. These questions that are worth 6 marks are often divided into different levels, 1, 2, and 3, and you have to get through the first level to get to the second level and get through the second level to get through the third level. So how would you do it? Well, they told you that we've got silver nitrate. So if you add silver nitrate, you'll form precipitates. They haven't mentioned adding acidified silver nitrate. I think from the question they are implying that there are another ions present there that could interfere and give you a false reading. But I don't think there'd be any harm in suggesting adding nitric acid and silver nitrate. We form 2 precipitates, silver chloride, silver bromide. You're not really going to be able to tell them apart very well, but you need a way of removing the silver chloride but leaving the silver bromide, and this is where ammonia comes in. We talked about this before. Dilute ammonia will dissolve silver chloride but not silver bromide. The equation you may not have come across yet, you might not have done this yet, but you will do. You'll have looked at this before the end of the year. So if you dissolve off the silver chloride, you're left with a precipitate of silver bromide. You can filter it, you can wash it with distilled water to remove any water-soluble compounds, and then you can dry it. So that's quite a good illustration of how the idea that you've come across for practical that you've done, determining the presence of chloride, bromide, and iodide, could be applied to actually separating silver chloride from silver bromide. It's probably that little bit of thinking outside the box that they are looking for in their practical questions. So we'll just have a look at 1 or 2 more examples before we wrap things up. Okay, 6.1. This one's worth 8 marks. This is a pretty huge question. Reaction of calcium compounds, pure solid, thought to be calcium hydroxide, can be identified from its relative formula mass, which can be determined experimentally by reacting a measured mass of pure solid, excess of hydrochloric acid, reaction given. The unreacted acid can then be determined by titration of standard sodium hydroxide solution. Be provided with hydrochloric acid, outline giving details how you conduct an experiment to calculate accurately the relative formula mass of the solid using this method. So it's a back titration. And I know that back titration is one of those examples that some people don't like very much. Oh, I've just noticed a question came through that I didn't notice before. Question before, the error have to be multiplied by more than 2 because the titer was an average. Oh yes, I said it was an average in my question. Okay. tell you what, I'll come back to that at the very end once we've gone through this. So if you stay on the line at the end, I'll cover that question then. So this is quite a back titration question, quite a detailed question, worth 8 marks. So you've got to dissolve the calcium hydroxide in excess hydrochloric, and then you're going to have to titrate the excess hydrochloric and work backwards from there. So what would the mark scheme say for 6.1? Here we go. Again, 3 stages. Appreciate the acid must be in excess. Calculate an amount of solid that permits this, or a statement that must be in excess of acid. You can work out the moles of acid in the acid that you've been given. 2 moles of acid react with 1 mole of calcium hydroxide. It's from the balanced equation. Therefore, the moles of solid weighed out must be less than half moles of acid. Yeah, otherwise the acid won't be in excess. So you can determine that the mass of solid must be below a particular value. So what would you do? Weigh the amount of solid in a conical flask. So you would add your solid to your acid. There will be acid solution left over. Titrate with sodium hydroxide. Record the volume when an added indicator changes colour. Calculate the MR from the experimental data. While your moles of calcium hydroxide is going to be derived from the titer. The titer will give you the amount of hydrochloric acid that's actually reacted. So eventually you will get through to your actual value of your MR. What I suggest you do is have a look at this question for yourselves and work your way through it. And just make sure you're reasonably confident with it, because these 8-mark questions are not very common. They do come up from time to time. We've been on the line for quite a while now, so I'm not going to go through the whole thing, because I think it would just take a little bit of a while, and I think you're probably getting to the point where during your half term, after an hour, you probably had quite enough. What I suggest you do, I'll take you back to the questions in a minute. These are all available online. If you want practice of exam style questions which relate to the practical work that you've done, these are very, very good examples. You can pause the video and make a note of them and go through them as part of your revision. So that's what I would suggest that you do. Okay, so I think what we'll do, we'll wrap things up there. I'll stay on the line for a couple of minutes. So if any of you have any more questions, you can ask me the questions. I'll stay on the line for a little while. I'm just going to go away for a couple of minutes. So I'll be back on in a couple of minutes' time. I hope you found this useful. I hope you found the existence of the practical handbook useful. If you're ever wanting to go back and check a practical that you've done before, just find out a little bit more about it, it's a good place to go. Hopefully you've got a better, clearer understanding of how to work on your error calculations. This video clip will be posted on YouTube, so you can have a look at it in your own time. So I'm gonna just go for a couple of minutes. If you haven't got any more questions, then feel free to be on your way. If you have got a question, just stay on the line. I'll be back in a couple of minutes. Okay, all the best. Enjoy your half term. I'll talk to you soon. Okay, I'm back again. Some people still on, so let's just deal with a few questions. Can I put this on the BLE? Yeah, I can put the presentation on the BLE, no problem. When do we double the percentage error? Is it just if you've taken a measurement? Essentially, yes. If for a piece of equipment where there is a start reading and a final reading, and you have to measure both. So burette, you have your start titer, your end titer. If your uncertainty is 0.05 for your start and your end, you have to double it. So rulers, burettes are two pieces of equipment that you're going to be most concerned with. Yeah, I'll send a link to the video in good time. And the question that was asked earlier on, yeah, I said it was an average in the thing. I didn't mean to do that. I didn't mean to say it as an average. That was my mistake. It was meant to be just a sort of single standalone value based upon two separate measurements. When you take an average, it gets a little bit more complicated working out what the percentage error is. It's actually in the handbook, so I'll bring up the handbook again to show you this. They do detail it. Let's have a look. So yeah, they give an example here where if you use the average of two values, so say 1.22 and 1.32, the uncertainty between the two is 0.1. So they're given an uncertainty in that example of being 0.05. If that is bigger than the uncertainty of the equipment for each reading, then that's the value that you are meant to take. Now, actually, I don't expect you to have to deal with anything that's quite that complicated. So I don't think you have to worry about it too much. There's another example here. Probably physicists maybe have to deal with this thing a bit more. So measuring the diameter of a wire, 0.37 and 0.34 are the values that have been taken. So the exact value for the mean is 0.355. The difference between the two is 0.03, so the uncertainty is taken as being 0.015, half of the difference between the two values. But of course, because you're measuring to two significant figures, you should really quote values to two significant figures, so you can range. But like it says, it's a simplistic analysis. So given a percentage uncertainty like this would be acceptable. I don't think you have to get too bogged down with this, because it actually tells you here on the uncertainty exams bit, where possible, questions in the exams will be clear on whether students are being asked to calculate the uncertainty of a reading or a measurement or given data. Where there is ambiguity, marked schemes will allow alternative sensible answers and credit clear thinking. So if you demonstrate a sensible understanding of what uncertainty is based upon the work that we've done, you shouldn't really have anything to worry about at all. So yeah, I can see how I confused things by mentioning in the presentation it was an average. it wasn't meant to be. So hopefully that's cleared that up. More questions come through. Would it be incorrect to add the 2% errors of the start and end measurements? Let me see if I understand this question correctly. So if you worked out the percentage error for the start value as a standalone value, and then the end value as a standalone value, and then added them together, that would give you the wrong answer. The idea is that you're meant to work out the difference between the two, the start and the end, and then apply the error doubled for measurements. That's what you're meant to do. Hopefully that clears that question up. There are some of you still on, which is absolutely fine. If you're still thinking things through and you've still got some questions, that's great. Again, I'm just going to go away for a couple of minutes and I'll come back. If there's anybody still here, you've got a question, fine. I'll answer more questions if you have them. If every question that you've got for the time being has been answered, then feel free to leave the room. You can always ask me next week when we're back in school. Okay, looks like most people have left the meeting now. I will stay on the line for a few more minutes if you've got any more questions, but for the benefit of anybody out there who is watching this video clip on YouTube, just refer you back to my website, which has lots of useful tips and resources for your chemistry, in particular my blog, which has a few I hope useful items that you might be able to make use of. The thing that I referred to in the presentation before was the organic functional groups, which I've detailed here for you. So you can see all the different tests here. And I've summarized them on this table along with the chemistry behind them as well. So hopefully there are things there that you can that you'll find useful. So what I'm going to do, I'm going to close down this meeting now. I'd like to thank you all for attending. Thank you very much for the positive feedback that you sent me. We may do more things like this in the future, just sort of check my website for information as it comes up. I'm going to close down the meeting now. Thank you very much. I hope you found it useful. and I'll see you soon.